Okay, in this video and the next two, we're going to talk about anatomy and physiology of the kidneys. And the kidneys are actually pretty remarkable. At rest, they receive about a quarter of all of the cardiac output. And that means that every day they're filtering about 1,700 liters of blood. And that also means that all of your blood is filtered more than 300 times every day. And what you can see up here is you can actually see a scanning electron micrograph of a nephron. This is the filtering unit of the kidney, as we'll find out later on as we go along. And so this is pretty remarkable, to be perfectly honest. Now, think about each of these and think, what would happen if the kidneys weren't working? Would you get changes in blood pressure? And you should automatically have said yes, you would, because you know the kidneys can sense a drop in blood pressure and then they produce renin, which is part of the renin, angiotensin, aldosterone system that we've talked about at least 10 or 15 different times. And so, yes, would they have an impact on acid-base balance? Well, in fact, they do. And in the long term, they're more important than respiration. So, you know, respiration can also affect acid-base balance, especially after the lab the other day. But the kidneys play a role in more long-term acid-base balance. They help to get rid of or reabsorb protons or bicarbonate ions, either or. Accumulation of wastes, absolutely. One of the most important things that the kidney does is to get rid of bad stuff. And so it does help to get rid of waste. And if they weren't working, then you would have an accumulation of wastes. And anemia, again, everybody should be all over that and say, oh yeah, the kidneys produce EPO, erythropoietin, which stimulates production and development of red blood cells. Well, no EPO, you don't have enough red blood cells, you have anemia. Well, what is the primary function of the kidney? The primary function is actually to regulate extracellular fluid environment of the body, and that includes both the volume and the composition. And you know that there are three major fluid compartments. You might not remember: intracellular fluid, and then the blood plasma and the interstitial fluid. And the three are in communication, so we change one, we get changes to the other two. And so the kidney is also important in homeostasis, as it adjusts the urinary output of the extracellular fluid compartment constituents. And so that would be all things, as we'll look at in just a minute. The kidney helps to get rid of surplus of certain things. And so an example would be protons and potassium ions. Those aren't the only things, but they're just two good examples. And it tries to help make up for a deficit. And so if you're low in something, it tries to limit the loss of water. It can't cut it down to zero. We're not like a desert rat, which excretes urine in solid pellets. And it also reabsorbs the vast majority of the sodium that you get, even when you get too much in your diet. You still reabsorb about 95% or more of all the sodium in your diet. The kidneys actually compensate better for an excess than they can for a deficit. And you know that if you're dehydrated, the kidneys by themselves won't fix that. You've got to actually drink more water to get it fixed. What things are regulated by the kidneys? Well, one of the major things is the blood osmolality, how much solute is in there. And blood osmolality is a little bit under 300 milliosmoles. Well, if it's regulating osmolality, what else is it regulating? And you should automatically say, well, blood volume. Osmolality is too high, then we need more water to come in. And osmolality is too low, we need to get rid of water. Well, you also know that blood pressure is directly related to blood volume. So blood volume goes up, blood pressure goes up. Again, different for gases and liquids. In gases, it's an inverse relationship. In liquids, it's a direct relationship. It also helps to regulate the concentration of plasma electrolytes, which we've been talking about since early last semester. And so here are the major electrolytes or ions that we care about: sodium, potassium, calcium, magnesium. You can read these. And so very, very important. I've highlighted potassium because if you're hypokalemic, what can happen is you actually get a depressed resting membrane potential. That actually makes it harder for you to activate muscle fibers, and that can actually present as muscle weakness. If you're hypokalemic, it can have a major impact on the heart, and you get a decrease in heart rate and a decrease in stroke volume. And again, that can be a very serious thing. The kidneys are helping to regulate plasma pH. Again, overall, more important than the lungs. The lungs play a role through that carbonic anhydrase reaction, but so do the kidneys. And again, you know that the protons will alter the pH, and bicarbonate and protons kind of go together through that carbonic anhydrase reaction that we've talked about. We just mentioned that you have to get rid of wastes, and the kidneys help to keep the concentration of wastes in the blood nice and low. Most of these things are byproducts of metabolism, can include ammonia, urea from breaking down protein and amino acids, uric acid, and even creatinine. Uric acid is interesting because when you have a buildup of that, you get hyperuricemia, which is actually what happens in gout. Gout used to be a disease of the Middle Ages that we would see in the royal families because they would have a diet that was high in meats. They would drink lots of sugary drinks. They'd have a lot of alcohol, and so you'd see a lot of gout back then. You also see an increased risk of cardiovascular disease, type 2 diabetes, kidney stones. Interestingly enough, we've seen over the past 40 years or so an increase in gout again, and it's because people are drinking too much alcohol and their intake of sugar is too high and they're becoming obese. And don't ask me why, I'm not sure, I haven't looked into the reason, but I do know that people of Japanese descent have a greater risk of developing gout than other races would have. Okay, other functions of the kidney. And so, again, we've already mentioned that the kidneys secrete EPO, erythropoietin, and renin. But the other thing that the kidney does is it converts vitamin D to its active form, 1,25-dihydroxyvitamin D3. And this helps with absorption of calcium from the foods that you eat and reabsorption of calcium from the kidney. Helps to get rid of foreign chemicals, and this could be drugs, medicines, or illicit drugs, pesticides in foods or things that you get, and then even food additives. And the people who make foods are all the time adding additives, which aren't necessarily good for you. The kidney also plays a role in maintaining blood glucose. Well, number one, the kidney has to use glucose to meet its own energy demands. Number two, as we've said multiple times, the kidneys are going to try and reabsorb 100% of the glucose from the filtrate. We don't want glucose in your urine. And as long as you're not getting too much glucose in your diet, the sodium glucose linked transporters are going to go ahead and reabsorb all the glucose. And here you can see that process. Over here, this is the filtrate. Sodium is going to move into the cells going down its concentration gradient, and as it does, it drags the glucose with it. Now you know that this is also secondary active transport because we do have to pump the sodium out of the cell, and that's an active process that requires use of ATP. And then, particularly if you're fasting, the kidneys play a role in making glucose, and so they help with the gluconeogenesis. Gluconeogenesis is primarily the job of which organ? And of course, everybody said the liver, right? Josh, good job, way to go. So yes, indeed, the liver. Organs of the urinary system, well, obviously, the two major organs are the kidneys. And the kidneys are producing that urine, and the urine has to be carried away from the kidneys through the ureters, which we'll talk a little bit more about a little bit later on. The urine is stored in the bladder. The bladder has the ability to expand and stretch, and so you can store urine until you have to get rid of it, and then you expel it out through the urethra. Kidneys are located approximately between T12 and L3, roughly. And obviously there can be a little bit of difference. You notice here that the right kidney is actually just slightly lower than the left kidney, and that's because right here is the liver, and it's pushing the right kidney down a little bit. And so that's an interesting difference. The other thing is that the abdominal aorta is over here, and so the renal artery to the left is slightly shorter than the renal artery over to the right. Not a big deal. I don't really care too much about that. And then each kidney is roughly the size of a large bar of soap. This might be just a tad bit small, but it gives you a rough idea of how big those kidneys are. And so again, for them to get 25% of the cardiac output at rest is pretty remarkable. What does it mean to say that your kidneys are retroperitoneal? Oh, the peritoneum, remember that guy? And so the kidneys are actually up against the posterior wall of the abdominal cavity, and that peritoneum is covering the front of them, but not the back. The kidneys actually have several layers that help to cover them, and you should be able to easily say that this must be posterior because here is, oh, look at that, lumbar vertebrae number 2. So that's got to be the back. Oh, here's the stomach. That must be the front. And then again, here's the spleen, and here's the liver. And you can see how it does kind of push up against the right kidney and push it down a little bit and actually change it. It's slightly closer to the spinal column. Well, we've got a couple layers of fat surrounding the kidney. One is perinephric, and so here it is here. It's this outer layer. You have to look closely. I hope this shows up on the video. But then we have this thin layer of renal fascia. It's this white layer right here. I hope you can see that. Oh, there it is. And then closer to the kidney, underneath the renal fascia, there's a second layer of fat, which is called perinephric, around the kidney, perinephric fat. And then finally, you can see this white layer of connective tissue that's right up on top of the kidney surrounding it, and this is a fibrous capsule. And again, it's a nice, strong connective tissue that helps to protect this guy. Now, in people who lose fat very rapidly and lose too much of it, they lose some of this perinephric and perinephric fat, which is helping to hold the kidney in place, and the kidneys can actually drop a little bit. And when they do that, we actually get a kinking right here in the ureter, and that means that urine can back up into the kidney and cause some pretty severe damage to the kidney. So that can be problematic as well. All right, well, look at the kidney. What do you see? And you should say, oh my gosh, wow, the kidney. It looks a little bit like the adrenal gland and also like the brain, right, Ross? And so you should say, when I look at this, oh, I see an outer layer, which I'm going to call the renal cortex. And then I also see an inner layer, which I'm going to call the renal medulla. So there you go. So like the brain, like the adrenal gland, we have a cortex and a medulla here. And then the renal medulla, you can see, is divided into these darker structures that two-dimensionally look like they're triangular, but three-dimensionally they're more pyramidal shaped. And so here you can see one renal pyramid. And you can see in this cross-section there are 1, 2, 3, 4, 5, 6 of those renal pyramids that you see there. And they're divided by these renal columns. So in between the pyramids, you can see the renal columns. And then down here at the bottom of the pyramid, you can see it leads into this tubular stuff. But the bottom of the pyramid is a nipple. It's not really nipple-shaped, but papilla means nipple. And the urine comes down through that into the beginning of the tubule of the kidneys. All right? And the kidney is organized into 8 to 15 renal lobes, and the lobe here is shown in this pale dotted line. And so here's a renal lobe. It includes the pyramid, part of the renal column, the papilla down below, and some of the cortex up above that pyramid. And so there's one renal lobe. And so again, you've got about 8 to 15 of those in each of your kidneys. The renal sinus, you can't really see it in this picture, but you can imagine where it is. It's underneath this tubular structure that they're showing here. And so it's this medially located depression in the kidney. Here's where the renal artery comes in and the renal venule is leaving. And so that's what we have here. And we see that we have these different pieces. What we see up here are minor calyces. This is a minor calyx. That's what it is. And so at the bottom, underneath the papilla, we have a minor calyx. And we've got 8 to 15 of them. The plural of calyx is calyces. And then the minor calyces will dump into major calyces. And so we have 2 to 3 major calyces that you can see here. And the minor calyces are dumping into those. And then finally, the major calyces dump into the renal pelvis, and this bigger tubular structure made up largely of connective tissue covered with epithelium. And these just help to serve to direct the urine from the pyramids all the way to the ureter. Okay, and the ureter, again, is that tube-like structure. It's like a very small hose or a straw or something like that. And when you think about it, the ureter is actually made up of several layers. Starting from the outside and in, we have an outer fibrous connective tissue layer. And so what you see here is connective tissue. Underneath that, we have two layers of smooth muscle. We have one that goes around, and so it's a circular layer, and then we have a second layer that runs along the tube, and it's a longitudinal layer of smooth muscle. And the smooth muscle, not surprisingly, is going to help to move the urine down to the bladder and help to push it into the bladder. And then lastly, the inner layer is covered with an epithelium, and that epithelium is going to secrete some mucus to help to lubricate it and allow the urine to move along through the tubule very quickly. Again, what's this beige region that you see here? And so you should be saying, oh, the beige region, that's the renal cortex, right? And so, good job. And so the salmon region that you see down here, you should say, oh, well, that's the renal medulla. And so again, that's correct. You can see the cortex and the medulla here. And then we can see again the major filtration unit of the kidney. That's really what the focus here is. And you might remember from reading or from what I said on the very first slide, that's actually the nephron. Here you can see the nephron. There you go. And so we've got two major parts of the nephron. And the first major part is the renal corpuscle. The corpuscle has two parts to it. The glomerulus is this capillary, and this is a very leaky capillary. And so we've got afferent arteriole leading into the capillary and efferent arteriole leading out of it. And then the second part of the capillary is the glomerular capsule, which is epithelium with connective tissue underneath it. And we'll look more detail at that. Again, here's the blood flow coming into the glomerulus through the afferent arteriole. Here's the blood flow leaving through the efferent arteriole. And then the second part of the nephron is the renal tubule. It starts right here coming off of the glomerular capsule. And you can see that it's this tubule that's all bunched up or convoluted. And so it's the proximal convoluted tubule. And then we move into this hairpin loop. And so this is the loop of Henle. And you can see that the filtrate is going to move down this way and back up the other side. And we get into another convoluted tubule, but it's further away from the capsule. And so not surprisingly, it's the distal convoluted tubule. The distal convoluted tubule dumps into this little piece of tubule, which is called the collecting tubule. And then finally, the collecting tubules, you can see several of them here, are going to dump into the collecting duct, and the urine is going to be conducted down towards that papilla and into a minor calyx, as we identified in the previous slide. And then here's a structure that we'll talk about in a little bit. You can see that that distal convoluted tubule comes up in between the afferent and the efferent arteriole. We call this a juxtaglomerular apparatus, and we'll talk about that later. Here you can see the nephron has been flattened out so that you can see the epithelium of it. And so you can look. And when you look at this, you say, well, the epithelium is pretty much all simple. There's only one layer all the way through from the capsule all the way through to the collecting duct. Okay? You can see that the majority of it is actually cuboidal, and so cuboidal here in the proximal convoluted tubule, cuboidal at the beginning and the end of the loop, and cuboidal here in the distal convoluted tubule, the collecting tubule, and the collecting duct. You can also see as you look here that most of the cuboidal cells have microvilli on them. And you know the microvilli are going to help to increase the surface area quite a bit. Since a major job here is reabsorption, that helps you to understand how we're going to reabsorb all of this stuff. There are two parts to the loop of Henle, and you might think it's the cuboidal and squamous cells, but it actually isn't. The filtrate is moving down along this side of the loop, and so that's the descending limb of the loop. the filtrate is moving back up over here, and so that's the ascending limb of the loop. And so that's what we mean. And both descending and ascending limbs have a thick part because of the cuboidal cells and a thin part because of the squamous cells. And if you look really, really carefully at the epithelium here in the distal convoluted tubule versus the epithelium in the proximal convoluted tubule, you should see that these cells are a little bit more highly developed and they have more microvilli here. And when you think about it, you should figure out that that means that most of the reabsorption is going to occur over here in this part of the nephron. And then finally, as I already mentioned, here's the collecting duct. And you can see that aldosterone and ADH work on the later part of the nephron and work here in the collecting tubule and the collecting duct to insert aquaporins or to insert sodium channels. One of the major differences here between the descending and the ascending limb is that the descending limb has lots and lots and lots of aquaporins that don't depend upon ADH. We reabsorb the majority of the water from the filtrate, and so we have aquaporins all along here that help with that reabsorption, and again, they do not depend upon the ADH. Juxtapose, neat word, huh? It means to place side by side. And so we're going to place this thing right here next to the glomerulus. And so that's why we call this the juxtaglomerular apparatus. Tough word, huh? Juxtaglomerular apparatus. There it is. There's the juxtaglomerular apparatus. It includes a part of the afferent arteriole and a part of the distal convoluted tubule. Here it is. Distal convoluted tubule coming up in between afferent and efferent arteriole. And you look at the afferent arteriole, and here you can see the endothelium, which of course is important, but then you can see a layer of cells here as well. And those are known as granular cells. Those granular cells are actually where the renin comes from. We've talked about renin hundreds of times now, right? Another difference that you'll notice when you look here is that the afferent arteriole is bigger than the efferent arteriole, and we do more vasoconstriction, vasodilation here to regulate how much blood actually gets into the glomerular capillary. Again, the pale green stuff represents the movement of filtrate, and the filtrate is moving along through here, and finally it's going to move into the proximal convoluted tubule, and there you can see those cuboidal cells with microvilli on the surface of them, and this filtrate is in between the visceral and the parietal layer of the capsule. Look at those epithelial cells that we see there. Very nice picture. Whoops, sorry. And so here again we can see the picture that we just saw showing the juxtaglomerular apparatus, the glomerular capsule, and the glomerular capillary itself. Here you can see a little bit different picture of that. And so here what they've done is they've cut into that glomerular capillary so that you can see the blood that's in there. And we can also see the afferent arteriole. Here are those granular cells. What comes from the granular cells? Oh yes, renin comes from those granular cells. And then there's the efferent arteriole. And then these are specialized epithelial cells that are called macula densa cells. They're actually able to sense the sodium chloride that's in the filtrate, and they can stimulate an increase in the reabsorption of sodium if we need to. This shows you the blood supply to the kidney, and I'm only going to make you learn a little bit, not very much. And so again, we have a renal arteriole coming in, and we have a renal venule that's leaving. This is very quickly going to move into a vein and go right to the inferior vena cava. This one is coming directly off the abdominal aorta. And then again, we get in here and we have the afferent arteriole leading into the glomerular capillary and an efferent arteriole coming out, which is, again, unusual. That's not usually what we have happening. Usually when we come out of a capillary, we go directly into a venule, then a vein. You can see as you look here, there's another capillary. The glomerular capillary is not responsible for the internal respiration of the nephron or the kidney. There's no O2 being extracted here, and there's no CO2 being picked up. You can see that that's going to happen later on. This is what's known as a peritubular capillary or the vasa recta. Vasa recta, as we'll see here. So again, there are the afferent and the efferent arterioles associated with the glomerular capillary. There is the capsule itself, which again is epithelium and connective tissue. And then again, here is that peritubular capillary or the vasa recta, and you can see that it is responsible for internal respiration here deep inside the kidney. So we are extracting O2 and we are adding CO2 to the blood as it moves through the peritubular capillaries. And as we'll see later on, this also plays an important role in reabsorption of water and lots of solutes as well. And then again, here's the distal convoluted tubule leading into the collecting tubule and finally the collecting duct. And again, as we said, here are the sites where aldosterone and ADH are going to work. And so again, as I've mentioned a couple of different times now, the pale green arrow represents movement of filtrate. And so the job of the kidney, well, number one, you have to form that glomerular filtrate. And so again, this is very much like interstitial fluid. And as we'll see in the next video, the forces that form the filtrate are the Starling forces. Way to go. Good job, everybody who said Starling forces. So it's exactly the same thing that was causing that interstitial fluid formation that we talked about before. Well, once we form the filtrate, we want to recapture all the good stuff. Oh yeah, tubular reabsorption. And you can see that tubular reabsorption is happening all along the way in the proximal and distal convoluted tubule, but also in the descending and ascending limbs of the loop, and even over here in the collecting duct. And then we have to get rid of some of the bad stuff. Unfortunately, we can't get rid of all of the bad stuff in the filtrate, and so we do have to add some of that in as the filtrate moves through the nephron and across through the collecting tubule and the collecting duct. And again, you can see that secretion also happens at all of those different places. And that brings us to the end of this particular video. And in the next video, we're going to really focus a lot on formation of filtrate. And so I'll talk to you later.